Here is a save file with 0 progress. The player starts a brand new game, watches the opening, and a few minutes later does something that should be impossible. They drive to a casino. They place some bets on a wheel of fortune. They walk away without ever spinning it. And about 40 minutes later, the credits roll. They did not play the game. They reprogrammed it. This is the story of how a gambling minigame becomes a tool for writing code into Grand Theft Auto, San Andreas, and how that lets a runner jump from the second mission of the game straight to the last one. First, the goal. The speedrun category here is called any%. The rules are simple: reach the end credits as fast as possible, by any means the game allows. There is no requirement to play missions honestly. A normal playthrough of this game runs on the order of 30 hours. The world record we are dissecting reaches the credits in 44 minutes and 43 seconds, so the entire campaign collapses to a single question: how do you convince the game that its final mission, end of the line, just finished, starting from a fresh save? Everything that follows is the answer to that one question. And the answer is not a cheat code. Not one byte of it is code typed by hand. The whole thing is a software exploitation chain carried out from inside the game's own rules, using nothing but the inputs the game already hands the player: a keyboard and a mouse. To understand the exploit, you have to understand one thing about how these games are built. The missions are not hard-coded in C++. Instead, the game ships a compiled bytecode program, a file called main.scm, and it runs that program on a small interpreter built into the engine. A virtual machine. Think of it as the game's own embedded scripting language. That virtual machine runs many cooperative threads, and every thread has a program counter, a pointer to the next instruction it will execute. Each frame, the engine walks every thread, read the opcode at the program counter, decode it, execute it, advance past it, and repeat. That fetch decode execute loop is the machine we are going to hijack. Now look at how a single instruction is encoded, because the format itself is the vulnerability. An opcode is a 16-bit number, 2 bytes, stored little endian. The top bit is a flag that inverts conditionals, the rest identifies the operation. After the opcode come the operands, and here is the clever, fatal detail: every operand is preceded by a single type byte that tells the machine what kind of value follows and, crucially, how many bytes to read. Type 1 means a 32-bit integer follows. Type 2 means a global variable. Type 4, an 8-bit integer. Type 6, a float. So instructions are variable length, and their length depends on the bytes you are reading. Hold on to that, because it means where you start reading changes what the bytes mean. We will weaponize that later. Next, the variables. Every global variable in the game lives in one contiguous block of memory. On this exact build, that block starts at a fixed base address, and each variable is a 4-byte cell. So the address of global number n is just the base plus 4 times n simple. But here is the architectural sin that makes the entire run possible. That block of variables sits inside the same flat byte space that the virtual machine treats as program. To the interpreter, a variable storage and an instruction byte are the same kind of thing. There is no separation between data and code. No bounds checking on the program counter. No memory protection. If you can make the program counterpoint at the variable block, the machine will happily read your variables as instructions. That single design decision is the bridge from writing a variable, which the game does constantly and safely, to injecting code, which should never be possible. A precise word on what kind of exploit this is, because the runners are careful about it and so should we. This is not arbitrary code execution in the classic sense. We cannot run native x86 machine code. We can only make the virtual machine execute opcodes that already exist in its instruction set, and we can only jump within roughly the first 24 kilobytes of script space. So it is constrained. The correct name is arbitrary script execution, or, as the community calls the jump primitive, arbitrary jump in script, AJS. But do not let only script fool you. That instruction set includes start mission, set variable, jump, and teleport the player. With an arbitrary write and an arbitrary jump, you have everything you need to script the ending of the game by hand. The full exploit is a chain of 5 separate bugs, and it works only because all 5 line up. Bug 1, a corruption that strands the player on mission 0, which quietly removes the game's guardrails. Bug 2, the Wheel of Fortune, which gives a way to write attacker-controlled bytes into script memory. Bug 3, an integer-overflow that lets the runner forge the exact byte values needed. Bug 4, a pointer overlap that hijacks the program counter and aims it at those bytes. And Bug 5, a payload, built to survive byte alignment, that executes a single jump into end of the line, the final mission, the end of the game. Let us take them one at a time. Bug 1. Early in the run, a memory corruption leaves one specific flag stuck on, the flag the engine uses to mean the player is currently inside a mission. The runners call the resulting state being on mission 0, and it is the foundation the whole exploit is built on, because it disables the game's safety rails. Consider what that flag normally governs. While it is set, the engine believes a mission is in progress, so it grants the mission script unusual authority and it suppresses systems that would otherwise interfere, autosave behavior, certain cleanup routines, and the normal locking of player control. Stranding that flag permanently in the on position means the game spends the entire run in a kind of privileged mode it was only ever meant to be in for a few minutes at a time. 2 consequences matter most. First, control. Normally a cutscene takes your input away. But with the mission state broken, the runner can answer or hang up an in-game phone call to snap control back to the real character, even in the middle of a cutscene. In the runner's own words, no cutscene is safe. That one trick erases enormous amounts of travel time and lets the run reach the casino city, Las Venturas, far earlier than the designers ever allowed. Second, broken side scripts. The same corruption derails other scripts that assume a sane mission state, and one of them, the stunt bonus script, starts behaving backwards. Hold that thought, because that broken script becomes a weapon in Bug 3. On its own, Mission 0 breaks nothing open. But it is the state that puts everything else within reach. Bug 2, and this is the heart of it. The Wheel of Fortune has 6 betting positions. The game has to remember how much has been wagered on each one, so it can display the bets and pay out, and it stores those 6 amounts as global variables, 6 4-byte cells in exactly the script memory block we have been describing. Now ask the obvious security question, what happens to those 6 values when the player walks away from the table without spinning? They should be cleared, reset to 0. They are not. The game simply leaves them sitting in memory. The only code that ever reads that region is the wheel minigame itself, and the player has just left it, so nothing comes along to overwrite the values. Those 6 leftover words are now attacker-controlled data at a known, fixed address. That is a clean arbitrary write into script memory, and you choose the byte simply by choosing your bets. But there is an obvious problem. The payload needs specific, large 32-bit values, numbers in the hundreds of millions. The player does not have that kind of money. So how do you place a bet worth $250 million when your wallet says 768? The answer is Bug 3, and it is the most elegant bug in the chain, a textbook off by one that opens the door to an integer overflow. In San Andreas, the only way to go into negative money is to borrow at a casino, and the player's gambling skill sets how far negative the balance is allowed to go. At 0 skill, the floor is -$100. Now look at how the game enforces that floor. It checks whether the balance is exactly equal to -100. Exactly equal, not less than or equal. That is the entire bug. A comparison written with equals is a tripwire stretched across a single value. It only fires if the balance lands on precisely -100. So the runner steps over it instead of onto it. Remember the broken stunt bonus script from Bug 1. Stunt jumps now subtract money instead of awarding it. A few stunts drive the balance straight through -100 without ever touching it, down to, say, -442. the tripwire never sees the exact value it was watching for, and the borrowing cap is simply gone. From there the runner borrows freely, pushes the 32-bit signed money counter past its positive maximum, and forces it to wrap, from the largest positive value all the way around to the most negative, and back up to anything in between. That is the forge. With controlled overflow, the runner can land the money counter on any 32-bit value at all, and drop that value onto a bet slot. One operator, equals instead of less than or equal, is the whole distance between you may borrow $100 and you may write any value you like into script memory. We can write bytes. That is worthless unless the machine can be made to execute them, and that is bug 4, the arbitrary jump itself, discovered by a runner named Theodoras. Here is the mechanism. When a mission script runs, the engine does not read it all at once, it streams it in chunks, and between chunks it pauses, holding a pointer to where it should carry on reading next. That saved pointer is, in effect, the program counter for the script. Theodoras found that if you start the mission just business at the precise instant the engine is paused mid-chunk on one specific page of the Big Smoke mission, the new mission setup overwrites that saved read position. When the engine carries on, it does not pick up where it left off in real code, it picks up at an address that lines up with a pointer leading straight into our block of leftover bet globals. In a single stroke, the program counter is now aimed at attacker control data instead of program code. And there is a second moving part underneath all of this, the engine's pool of in-game characters. When characters are unloaded, their pool slots are not freed straight away, a cursor walks the list and recycles them later. By controlling which object lands in which slot, the runner controls the exact pointer value that gets used, and therefore exactly where the hijacked program counter comes down. That is why this is the most fragile step in the whole run. It depends on game state, object lifetimes, and timing all agreeing at the same instant, and it is where the overwhelming majority of attempts simply crash to the desktop. Now the cleverest piece of engineering in the entire run. Recall two facts we established earlier. Instructions are variable length, and the exact byte the machine lands on when it enters our payload depends on that invisible fraction of a second timing from bug 4. In practice, the runner cannot know whether execution will enter the payload on an even byte or 1 byte off. So the payload is built to behave correctly either way, it is self-correcting. Here is the worked example straight from the run. The runner needs the value 768 sitting in a slot. In hexadecimal, 768 is 300, written into memory little endian, those bytes are 00 followed by 03. Now watch what the same 2 bytes do under the 2 possible alignments. Enter on the even boundary, and the opcode reads as 300, an opcode the game does not use, so it behaves as a no operation. Execution shrugs and steps forward, still in alignment. Enter 1 byte off, and the very same bytes decode instead as opcode 0003, shake camera, an instruction that takes 1 operand. Reading that opcode plus its single operand consumes an odd number of bytes, and that odd step nudges the read position back onto the even boundary. The visible symptom on screen is a tiny, harmless camera shake. The functional effect is that the misalignment has healed itself. That specific value was chosen because it is, at the same time, a no-op on one alignment and a self-realigning instruction on the other. It is exactly the idea behind a NOP sled in classic exploitation, only here it is expressed in the algebra of opcode widths. With alignment guaranteed, execution is finally walking the payload as instructions, on the right boundary. It runs through the zeroed slots and the filler bytes as harmless no-ops until it reaches the handful of opcodes the runner encoded as bet values, and the real payload is almost insultingly small. It does just enough to satisfy what the ending checks for, and then performs a single jump straight into end of the line, part 3, the final mission. Control lands inside the game's own ending sequence. The game plays that ending exactly as if the player had earned it, the completion flag is set, and the credits roll. Step back and appreciate the shape of it, 40 minutes of setup to construct an arbitrary write, a control flow hijack, and a self-healing sled, so that the very last instruction the runner executes is the game being told, in its own bytecode, to go to the end. A word on the human difficulty, because none of this is point and click. Buried in the setup is a timing window on the order of 25 thousandths of a second, in which the runner has to set an internal counter to an exact value, with nothing on the screen to confirm success or failure. The runner does not find out whether the input landed. They simply continue for tens of minutes and learn the answer only at the very end, when the jump either loads the final mission or crashes the game to the desktop. Documented routes count roughly 31 distinct, precise, often counterintuitive steps in the sub-hour run, several of them frame or timing sensitive. There is no checkpoint and no feedback. The runner commits, holds the entire structure in their head, and waits to find out whether the next thing they see is the credits, or a crash. So step back and look at the 5 defects as a set, because each one is a textbook flaw with a name far beyond this game. 1. Data and code share a single, flat, executable address space, variables and instructions are indistinguishable. In a modern report that is code injection, the failure to separate code from data, the same root class as memory that is writable and executable at once. 2. Nothing bounds checks the program counter, so a stray pointer can steer execution into data, an out-of-bounds control transfer, a sibling of the buffer overflow and out-of-bounds write classes that dominate memory safety bugs. 3. Sensitive values, the bet amounts, are left in memory after the minigame exits, never cleared, that is the sensitive data not cleared class, the same defect behind real-world leaks of keys and session tokens out of reused buffers. 4. An off-by-1 comparison, equals where the code meant less than or equal, opening a signed integer overflow, an incorrect comparison and a numeric overflow bug stacked on top of each other. And 5. A corruptible piece of global state, the mission flag, that, once stuck, strips away every guardrail at the same time. Remove any single one of these and the run falls apart. And not one of them is exotic. Confused code and data, missing bounds checks, secrets left in memory, off-by-1 comparisons, and corruptible global state ship in production software every week. A casino in a 20-year-old game is just an unusually elegant place to chain them all together. And that is the whole chain, a virtual machine with no separation of code and data, no bounds checking, and a self-describing, variable length instruction format, taken apart with a write primitive, a control flow hijack, an alignment sled, and a one-line payload, delivered entirely through a games casino. Enormous credit to the people who found it and explained it, Theodoras, who discovered the arbitrary jump-in script, Joshimas, whose root and breakdown this talk is built on, and the wider San Andreas speedrunning community, whose patient documentation made it possible to understand. Thanks for watching.